there. My name is Yash Savani. I'm a machine learning engineer at Reality Engines. Today morning, we're going to be giving a workshop on unsupervised learning and deep learning based forecasting. So the agenda for this talk is I will be giving a talk on anomaly detection first, and that's like a form of unsupervised learning. Then Sam will be giving a talk on deep learning based anomaly forecasting. Then after that, Austin will be showing off a workbook where you'll be able to train your own deep learning based forecasting model using our service at Reality Engines. And then finally, I'll also be showing a workbook where I'll be showing you how to train your own anomaly detection model too. Finally, Bindu will make some closing remarks. So, okay, I'll start by talking about anomaly detection. Anomaly detection is a very important field in machine learning because in the real world, data is never perfect, and it's important to identify where those imperfections are. Let's begin by discussing what an anomaly is. From a young age, I think we all have an intuitive idea of what an anomaly looks like. If I have 3 apples and 1 orange, it should be pretty clear that that orange is an anomaly. Armed with this intuitive idea, we can define an anomaly as a pattern in the data that does not conform to a well-defined notion of normal behavior. There are 2 key assumptions that we make whenever we consider anomalies. Firstly, they have features that differ significantly from normal behavior. This is the essence of what it is to be an anomaly. The more similar the anomalous point is to the normal data, the harder it is to classify as an anomaly. And the second assumption is that anomalies are rare. If they were not rare, then we could use classical supervised learning techniques to identify the hyperplane separating the anomalous data points from the normal ones. However, if the anomalies are rare, we cannot use these supervised learning techniques as shown in this diagram. So here you have a classical, if you have a lot of anomaly data points that are labeled, you can easily identify this circle as the hyperplane that can classify anomalous points from non-anomalous points. But in the case where you don't have labeled data or very little labeled data, it's much harder to come up with that hyperplane. Note that whether or not you have enough labeled data points is dependent on the dimensionality of the data. So this is a subtle point that we'll come back to later. Next, let's consider the different types of anomalies that are available. We classify anomalies into 3 categories. First is point anomalies. These are anomalies that deviate significantly from normal behavior, and they're usually easy to identify. So in this case, the red point here is an anomaly, and it can be pretty easy to identify that this is an anomaly. Second is contextual anomalies. Here, the anomalies are only anomalous when considered in context of the other data points. So here, maybe this red point would not be considered anomalous because you have other green points that are at the same level. But if you look at the context around it, it is considered an anomaly. And finally, we have collective anomalies. These are anomalies where multiple correlated features produce anomalous points simultaneously, but themselves, these anomalies might not be classified as anomalous. So here, these red points may not be considered anomalous, but together, because they deviate away from each other, away from the normal behavior, it'll be considered an anomaly. There are many applications to anomaly detection. Here I've listed a few. At Reality Engines, we have been exploring some of these, specifically fraud detection and intrusion detection. Here we try to identify fraud or intrusion based on anomalous user behavior in data logs. And the other one is time series monitoring. Here we try and identify anomalous time slices in a time series setting. In the final part of this workshop, we'll be using the Reality Engine service to create our own time series anomaly detector to identify anomalous cloud spend. Okay, so the general solution for any anomaly classifier is composed of 4 parts. The first part is to get enough data to train the anomaly detection model with. This is usually through a CSV or whatever like classical forms of data that you have. Second, we analyze this data using PCA, t-SNE, or any one of the dimensionality reduction techniques that are available. And any one of the dimensionality reduction techniques available. Third, we fit a model to this data. There's a vast corpus of models that we can fit to this task. However, the models I'm sure you are all most excited about are the deep anomaly detection models, and we'll be exploring one of these soon. And finally, we evaluate the model by giving both anomalous and normal data points to the model and seeing whether they can be labeled correctly as anomalies or not. This is a step where the analysis in step 2 will come in useful. So we'll be able to see which points are anomalies based on the analysis that we did before. Okay, so assuming we have already collected and analyzed some data, we now want to train a model that can classify the anomalies in our data. While there are several models we can use, there are 2 key benefits of using a deep learning model. Firstly, we do not need to do much data curation since the model will identify the best features to use automatically. Secondly, deep learning is especially well suited for high dimensional complex data with a lot of samples. Most practical use cases of machine learning fall into this category. So most of the deep anomaly detection models are based on conditional generative models like VAEs or GANs. The current literature has focused more towards the use of VAEs, though there are some papers that describe anomaly detection using GANs. Since there is more evidence supporting anomaly detection using VAEs, we will pursue a VAE generative model as the basis for our anomaly detector. A VAE or a variational autoencoder is a deep learning model that can be separated into 2 parts, an encoder and a decoder. The encoder takes as input a data point and encodes the data point into a location and a scale vector. An intermediary step then samples a new vector from a probability distribution with a location vector as the mean and the scale vector as a log variance. The decoder then takes this sampled random vector and then tries to recreate the input data point. The way we train a VAE is using something called an elbow loss function. So the way that works is the elbow has 2 terms in it. One is a reconstruction error, or how closely the generated data point resembles the original input data point, as well as a KL divergence regularization term that makes sure that the location and scale vectors do not deviate too far away from a unit normal distribution. So this was like a whirlwind tour of the VAE, and I've omitted a lot of details, but I would encourage you to use the links in the bibliography below to learn more about how these models work. But forging forward, we want to use these VAEs to actually train an anomaly detection model. So how do we do that? First, we train the model using normal or non-anomalous points. That is, we try to recreate these triangles on the left. So each triangle is passed to the VAE, and the VAE is trained to try and reconstruct that triangle. Then during the evaluation phase, we provide new data points to the VAE and attempt to recreate them. So we measure how good our recreation is using the reconstruction error. If the reconstruction error is high, then we classify that point as an anomaly. However, when we classify this point as an anomaly, and when the reconstruction error is low, we classify that point as normal. In this example, the VAE is accurately able to recreate the triangles since it has been trained on triangles. However, when we give the VAE a circle, it doesn't know how to recreate the circle and therefore incurs a high reconstruction error. The intuition here is that the VAE knows how to recreate points from the normal data really well. That is what it has been trained to do. However, if we see a data point that is very different from normal data points, it does not know how to recreate it. Therefore, it will do badly when trying to recreate the anomalous points, and we can use this badness as a measure of how far away the data point is from normal data. Now that you have a sense for how we can go about building an anomaly detection model using a VAE, it's also important to be aware of the kinds of data you're training the anomaly detection model on. This awareness will help you make the model more effective. While this is true for most machine learning problems, it's especially true for anomaly detection because this is an unsupervised learning task, and the tighter the model fit, the less likely it is that anomalies will slip through. So, keeping that in mind, there are a few things that you need to be aware of when trying to train these VAE anomaly detection models. Firstly, it's what type of data you have. If your data is sequential, then you might want to use an RNN. If you have an image, you might want to use a CNN. If you have a non-sequential tabular data, you might want to use a fully connected layer. These are pretty classical things you want to keep in mind, and they're very important when it comes to building these unsupervised learning models. And second, what is the dimensionality of your data, and how complex are the interactions? If your data is high dimensional and very complex, then perhaps you want to make use of a deeper neural network with NAS to optimize the architecture. And finally, if you do have anomalous data you can train on, how much labeled data do you have? If you have lots of data, then you could try to use supervised learning algorithms. And if you have none, then you might want to use anomaly detection. However, going back to that point I alluded to earlier, the amount of the number of training data points you have is dependent on the dimensionality of your data. So if you have very complex, high dimensional data, then because of the curse of dimensionality, you're going to need an exponentially larger amount of labeled data points to get the same to get like the same results from a classical supervised learning method than if you had a smaller, less complex data set. So yeah, so basically these are the things that you want to keep in mind when trying to train your anomaly detection model. This is all well and good conceptually, but I'm sure my hand-drawn illustrations have left something to be desired. So here's some code that I hope will be slightly more convincing to you that these models actually work in practice. So here we have some data that is sampled from a 3-dimensional S-curve. So here a picture is worth 1,000 words. You have an S-curve where data points that are along the S-curve are considered normal, along or around the S-curve are considered normal, and data points away from the S-curve are considered anomalies. So in the first step, we have actually gathered our data. The second step is to use PCA or some dimensionality reduction to visualize this data. So we've done PCA here, and as you can see, PCA has correctly identified the 2 dimensions. In this case, I think it's X and Y, to identify the 2 dimensions that can compress this data well. Then we go ahead and we train a simple VAE model. So this is a really simple 2-layer encoder and 2-layer decoder. So it's a 2-layer encoder and a 2-layer decoder that can encode this data. PCA would not work here to encode this data into 1 dimension because of its nonlinearities. But this is why we use deep learning, because deep learning can handle these nonlinearities with ease. So we go ahead and train this model on this underlying data, and we train it for around 1,000 epochs, and then we want to evaluate this model. To evaluate this model, we have a grid here. This grid is a 3-dimensional grid, and we want to see if the VAE can identify which points in this grid are considered anomalous and which points in this grid are not considered anomalous. So for instance, in this in a grid here, you'd want the points that are along the S-curve to be considered anomalous, and the points that are not on the S-curve, like something here maybe, to be considered anomalous. So yeah, so we go ahead and we use this model to do that. And here we have a slider that will help us interpolate between the least anomalous points to some of the more anomalous points. So here, as we can see, the VAE has been able to encode the S-curve. As you can see, as we slide to the right, more and more anomalous points show up. And as you can see, the VAE has encoded within its weights the data, and we can use this as a model to show which data points are anomalous and which ones are not. So things on the edge here, which are lighter and warmer in color, would be considered anomalous, while those in the center, which are closer to the S, would be considered non-anomalous. So yeah, in summary, anomaly detection is an important area of machine learning, because often we may need to identify if a point differs from normal without having access to large amounts of labeled anomalous data. There are many techniques that have been used to help identify anomalous points. The ones we've described today use a VAE model, where we train the VAE to recreate normal data points and then evaluate the reconstruction error on the test data points to see how anomalous they are. Yeah, thank you for listening. Now I'll hand it over to my colleague Sam to tell you a little bit more about deep learning for forecasting.
All right, 1 second.
Yeah, for the question around having access to the notebooks, yes, we'll publish those.
All right, can everyone see my screen?
Yes, we can.
All right, so I'm just going to give a quick overview of the definition of the forecasting problem. What are metrics? How do we distinguish between better and worse forecasting models? I'll discuss a classic algorithm, which is ARIMA, and then I'll just give a quick overview of the deep learning approach. Cool. So in general, in forecasting, we have a time series, which means just a sequence of numeric values. And given n consecutive of these values, we want to predict the next k. And we may have a single time series, or we may have a multivariate time series, meaning many parallel time series. So one example of a multivariate series is readings for like many electric meters, or maybe stock prices like the S&P 500 you can think of as like 500 parallel time series of price. So, and in addition, in the multivariate case, we may have additional features. So you can think of if there's one time series for each electric meter, maybe you also know like the location of each electric meter, or maybe in the case of stock prices, you have additional information about these companies. Yeah, and in general, you just want to predict the next k values. Yeah, so what are some challenges? So time series may or may not have a trend. If they don't have a trend, we say that they're stationary. A trend meaning in the long run, they steadily increase or decrease. So there's not a mean that they tend to. There may also be like complex correlations. So for example, in the case of financial data, correlations between stock prices are extremely complicated, and there are people that devote a lot of resources to untangling those correlations. There's also often periodicity, which may be very strong or weaker. So an example of this is in sales data, we are likely to have very strong weekly and yearly periodicity, because sales are highly dependent on day of the week, time of the year. And yeah, so here's an example of a strongly periodic time series with strong trend CO2 levels. Yeah, so what are the common metrics for these problems? We rely on two. So these are kind of intimidating looking acronyms, but they're actually not too complicated. So the first is NRMSE, or normalized root mean squared error. So you can see these equations. Taking the square root of mean squared error gives you something called the standard error, and we normalize it in the sense that we divide by the average time series value. So just rescaling it. And we also use SMAPE, which is like a variant of mean absolute error. So we average the absolute errors, but we divide them by the average of the true value and the predicted value. Yeah, so this is also like a rescaled version of like an L1 metric, or an absolute value difference metric. So they're complementary metrics because one uses the squared error, NRMSE uses the squared error, that will penalize large errors more heavily. So which one is more important to you kind of depends on your application. Like maybe you don't mind if you have like occasional large errors, as long as in aggregate the errors tend to average out. Yeah, so a classical approach to forecasting is ARIMA. So this is built up of a few different components. The most basic is what's called an autoregressive model, which is a linear regression regressing the current time series value on the previous p values. So that's useful if you have like a very strong periodicity, like a sine wave, for example. And if it's local, meaning it only depends on the last few time points. You can reduce the variance of this model by adding some noise terms, building what's called ARMA, or autoregressive with moving average. And yeah, and finally, because ARMA can't fit non-stationary time series, can't fit time series with a trend, the final addition is that we can replace the time series by its consecutive differences. And we can, if we do that enough times, the series is likely to eventually appear approximately stationary. So there are, at each of these steps, we introduced a parameter, P, Q, and D. And so that gives you a whole family of models for different values of P, Q, and D. And yeah, versions of this are very common in practice. Yeah, so what is the deep learning approach in a nutshell? So we build an architecture that has an RNN layer for the time series input. And then this goes through a neural network architecture, and it has K outputs for the K values that we're trying to predict. And as with other neural networks, we train this through backpropagation. And so the strengths of using deep learning for forecasting are that we can capture complex nonlinearities. You'll notice that like ARMA is linear in the previous terms and the error terms, for example. Whereas RNN can like build very complex dependencies and dependencies over a long time scale. And in addition to this, we can also easily incorporate other features. So for example, like in financial data, if we have these features associated with companies or stocks, you can easily build those into your architecture, as opposed to ARIMA just looks at just a numerical time series. So this can handle like large complexities, and it's also very flexible. You can add additional information very easily. Yeah, so that's just a quick schematic overview of the deep learning approach to forecasting. So next, we're going to get started on the workshops.
Yes, thank you, Sam. All right, here. So just confirm, can everyone see my screen? Excellent. All right, so quick introduction. My name is Austin Zellman. I'm a senior software engineer here at RealityEngines.AI. And today we're going to go through a workbook, which will allow you to set up a forecasting prediction engine using RealityEngines.AI, using the popular Rossmann store sales dataset. So we're essentially going to take a data set that's full of stores and their time-stamped sale history. So for each day, there's going to be an entry in the data set that contains how many items they sold, and we're going to train a deep learning model on that data and be able to predict the number of days into the future about how many items that the store is going to sell. And so to get started, I'm going to ask everyone to go to the link https bit.ly/R E forecasting FORECASTING. We're going to post this to the Slack channel as well as the Zoom chat just for your convenience. But we're going to give everyone just a moment to get to this URL. And so while you're navigating to this link, I'll just give a brief explanation about what the workbook is if you're not familiar. So in Google Colab has donated resources, computers for running Python inside of your browser. So you don't need to download Python. You don't need to set up your environment. Everything is going to be run in the cloud on this dedicated machine for free. All you need is a Google account. If you don't have a Google account, it's pretty quick to set one up. Just in the top right hand side of your screen, you can go ahead and click sign in or sign up. And so I'll give everyone about a minute now to navigate to the link. You'll sign into your Google account. And once everyone's done that, we'll go ahead and start moving forward with setting up your Reality Engines account so you can then run this notebook. And if you have any issues getting to this page or signing up with your Google account, please feel free to reach out on the chat. Again, we're available on the Slack. You can find the link once you're actually inside of this workbook. You can click on any of these links. We've got the Slack support channel link here. You can also just contact us directly on the chats inside of the Zoom. And yes, so I'll give everyone about another minute and a half to get set up here. And if you're already set up and are itching to get going, definitely definitely feel free to explore some of this notebook, but we'll be going through step by step through everything here. I'll call out some things, and again, if you get stuck at any point in this process, we're all here to assist in debugging your issues, because we want everyone to be able to walk out of this workshop with 2 different trained models. We're going to have a forecasting model, and then Yash is going to come back online and walk through the Anomaly workbook. So we're going to be using these workbooks quite a bit for the next hour or so. So definitely want to make sure that everyone is caught up and ready to go here. All right. So now we're going to go ahead and get started with this workbook. So if you still are behind and haven't set up your account, no worries. We're going to not have to run anything in the first few minutes here. So definitely feel free to jump in and follow the instructions if you're a little bit behind. But the first thing that we're going to do is actually create a RealityEngines.AI account and get an API key, which will allow us to run the rest of this workbook. So the first thing you're actually going to do is you're going to click on this special sign-up link. RealityEngines.AI is in a private beta. So you can't just go to our site and sign up immediately right now, but this special sign link will actually give you the ability to create an account. And so we're going to give you early access to our platform. So once you click on this link, you'll be directed to a free trial sign-up page. And so what you're going to do is just type in your name, email, and password. It doesn't need to be an email you can access, because we're going to send a verification email. If you want to skip that part of the process, you can use the sign up with GitHub or sign up with Google links. Both of these will allow you to immediately just jump into your account. But I'm going to go through and go ahead and sign up with my name and email. And definitely don't feel like you need to be in a rush here. We're going to take it slow, just make sure everyone is getting through this part of the process so we can kick things off on the right foot for the workbook. So I'm going to type in my email. And Safari will generate a strong password for me. All right, and so now that I've hit sign up, I'm now on the verify account screen. As I mentioned, you do need to verify your email address. And so you should receive an email within just a few seconds with a verification code. You can either click on the link in the email and they'll pre-fill in the verification code for you. Otherwise, feel free to just type in the 6-digit code directly into this box here. If you didn't receive the email, just check your promos, check your spam folder. It really only should take a second. If you still haven't received the email, make sure in here that the email is correct. I think most of the people who don't receive the email, they had a typo in their email address. And if you typed it in incorrectly, just go ahead and hit the back button. The back button will go back to the sign up page and you can sign up with your correct email address. Otherwise, if you're sure that it is correct, definitely just press the resend verification code. This will invalidate your previous code. So if you happen to get 2 emails suddenly in your inbox, make sure you use the latest one. But once you've received your verification code and verify your account, I'm going to go ahead and click on that button to verify my account. It is expired because I did type in the wrong one. So let me go ahead and enter in my correct verification token. There we go. All right, so I'm just going to go ahead and skip this skip the organization creation. Just go ahead and automatically generate an organization for me. So in Reality Engines, we have organizations are essentially your team. So you can invite your coworkers to join in and help train models, upload data sets, and manage your deployments. But the first thing that we're actually going to do here, despite the splash thing to create your first project, we're actually going to do everything inside of the workbook from here on out. And so we actually want to use the on the bottom half of the screen, we have a prompt asking if you want to use our API, and we definitely do. So we're going to go ahead and click on the link for the create an API key. And we're going to use this API key inside of our workbook. And so you'll be brought to this API key screen. You can go ahead and give it a tag if you want. So I'm just going to tag it that this is my workbook API key, as I'm going to delete this API key after this session, as you can all now see my API key. And so you definitely want to make sure you keep these API keys private and not broadcast them to the world, as it will allow you to create, delete projects, train models. And so this is your authentication key that you should keep inside of your own environment and for your development purposes. So you can highlight and copy this API key, or click on the copy, and that'll just copy your API key to your clipboard. And once you have the API key, we're going to jump back to the workbook page. And then if you lost this page, again, the link is up here at the top of the screen. It is again bit.ly/ capital R, capital E, lowercase forecasting. And now that we have an API key and an account, we can go ahead and get going with actually running the code. If you're a little bit behind, we have the authenticated sign up link right here in the prerequisites. Make sure you click on that link for the sign up. And then if you wanted to jump directly to the API key dashboard in case you lost your API key, this will take you directly to your API key list. You can go ahead and copy that key and then catch up with the rest of us. All right, so the first thing that we're going to do is actually start running the code. So we're going to install the Reality Engines API client. And if you're not familiar with Python or a little bit rusty, don't worry. We don't need to actually write any code for you here. We're just going to step by step go through everything, and I'll explain as we're going along. And so the first thing that essentially for this workbook, if you're not familiar, essentially we've got interdispersed between code and some explanation blocks, text blocks, so we can explain what we're doing at every step. But when we hit play here on the first code block, it's going to prompt you saying that, hey, this notebook wasn't authored by Google, it was authored by me, Austin at RealityEngines.AI. So you're just you'll hit run anyway to say that you trust that you trust the code that I'm running. All right, and so after hitting run anyway, it's going to download and install the Reality Engines API client onto this cloud machine. And then after that, we're going to also import some of the Python libraries, pandas, which is just a tool for previewing, and we'll use it for downloading CSV and JSON files, as well as PrettyPrint, which just formats output. And so it looks a little bit better inside of this notebook. Neither of these are required for running Reality Engines normally, but they'll be useful tools for our workshop. So I'm going to head and hit play on that box as well. And just a short note, throughout this process, all of these steps build on each other. So make sure that you do hit every box as we're going down. If you miss a step, the rest of the workbook will definitely not work. So make sure that you complete everything. If you do need to rerun a box, let's say you accidentally hit play on this box and setting your API key to nothing, you can go ahead and insert your API key and then rerun that box, and that'll make sure your API key is actually set. And so, as mentioned, there's a field here for your API key. So go ahead and hit paste from your API key dashboard. We also included a link here back to your API key dashboard and Reality Engines that'll take you to your API key list. And you can go ahead and paste it directly in here, hit play, as I had mentioned, and that'll set your API key, which will then instantiate the Reality Engines client. So the last thing that we need to do to get set up is to create, or to actually instantiate our Reality Engines client with our API key. So by hitting this, we'll import our client and then instantiate it. And so now we're good to go, and we're ready to start creating a project and training our model. So now that we're all set up, just to go into a brief highlight of the key terms here. So inside of Reality Engines, we've got projects. Projects essentially will encapsulate all of your data sets and define the use case. And so the use case is Reality Engines tries to solve specific business problems. And so we try to map your business problem to a use case inside of Reality Engines. And we use our industry expertise and deep learning models to specifically, or deep learning algorithms to specifically tailor the parameters and deep learning models to actually try to get the highest performing model possible to fit your business use case. And just to get a overview of all of the use cases available, you can go to RealityEngines.AI, or you can use the API client and you can list the use cases. So you can see all of the use case enums. We have a pretty formatted name and as well as a description for each of these use cases. And so you can navigate through and try to find the best use case that you're trying to solve for your project. In this case, as I had mentioned, we're trying to forecast our sales for stores over a time series. And so we're actually going to use the use case retail. And that's going to be our demand forecasting. So we're trying to predict how many items we're selling in the future. And so we're going to go ahead and set our use case to retail. So if you hit play in the next box, that will set the use case to retail, which we'll then use to create our project. But before we create the project, if you wanted to get a deeper understanding about the requirements for the use case project, we do have a describe use case requirements. On this API call, the output's going to be a little bit in depth here, but essentially what this boils down to is it's going to tell you what data sets are required in order to make this use case work. And inside of each data set, what kind of columns are we expecting? And so the first one here, we have the time series data set. So this is a required data set, and we need a few items inside of this data set. We need a date column. We need the demand, so the number of items or sales that you're trying to forecast. We have an optional column called future. And so future is like a holiday, something that we know in the future that's going to happen for sure, that we can then use to better inform our model about what's happening in the future, and it can use that info to better predict what's going to happen. So for example, if we know that our store is not going to be open on Christmas and our sales are going to be 0, we can tell our model ahead of time that, hey, on the 25th of December, it's going to be a holiday. I know that that's going to happen. And so it can then infer that, okay, given that it's a holiday, I'm not going to have any sales that day. And so we can use a lot of extra information to train a better performing model. And then we also have a column. If you have an extra data column inside of your data set, you can tag it with an ignore. And then finally, the item ID. And so this is just the unique identifier, say your store ID, that will use, or that will be available at every time step. So let's say I have 1,000 stores. I just number them 1 through 1,000. And I'll use that ID to associate it along with the time series. We also have a optional data set. and that's the item attributes, in this case, store attributes. This could be extra information about your store, say the square foot of the store, where it's located, what zip code, any extra information that doesn't change over time. If it changed over time, we'd put it in the time series data set. If it didn't, we can have a much smaller data set for the store attributes in this case. And all you need for this that's required is the item ID. So that's going to join on the time series. So if, again, the store number is 1 through 1,000, I just need my store number, and then any extra columns that you want to use inside of or for training and extra information about each store that would go inside of this data set. All right, now that I've given you a holistic view of all the requirements, let's actually go ahead and jump in and create our project. So the first thing that we're going to do here is use our Reality Engines clients. We're going to hit play on this. So this is going to create our project. We're going to give it a name of store sales forecasting, and the use case that we had set above, which is the retail forecast, or the retail. And so this is just giving us a reference, a project ID that we'll use going forward to actually upload our data sets to this project. So as I had already mentioned, we're going to upload our data sets now. So Reality Engine supports linking your AWS S3 buckets or your Google Cloud Storage, but we also allow direct file uploads, so you can store your files directly with RealityEngines.AI. So for this workshop, rather than going through linking your S3 account, we're going to just go ahead and directly upload from our workbooks. And so we have 2 data sets from the Rossmann data set. So we have the store sales history. So that's the time series, as I described above, which has the dates, the store ID, and some future information about holidays. And then finally, we have the store attributes. And so that's just a little bit of attribute data about each store. So let's go ahead and click on this next box here, which is to download the sales forecasting, or the sales time series. And so we're going to go ahead and download that, save it to saleshistory.csv. And you can see that, and then we're going to take a quick glance over the data set, and just so you can see the columns that we're going to be uploading to Reality Engines. So we've got about 844,000 rows. Each row contains the store ID. It has the timestamp. It has the number of sales. It also has the number of customers that came into the store that day. We have the state holiday, school holiday. So a lot of the information that I mentioned. And so you can see that for school holiday, it's just a 1 or a 0. State holiday, we actually have a few different categories. So you can go ahead and set multiple categories. So for each different kind of state holiday, say it's just a government holiday, you can tag it with A. If it's all the businesses take off the day, then you can tag it with another category. So we support both binary as well as multiple different types of holidays. You could even just use the holiday name if you wanted to.
Hey, Austin, sorry to interrupt.
Yes.
Is it possible you can enlarge the font or zoom in?
Oh, of course.
The font seems like quite small. It's hard to see. Okay,
yes.
It's much better.
Thank you for letting me know.
Great. Thanks.
Right. Yes. All right. I do apologize. I hope everyone can read this a little bit better. All right. So now that we have the data sets, again, just showing you the example data, we'll also download the store attributes data set. And so this data set is just one row for each of the stores. So we have 1,115 stores. We have categories for the store type, how far away it is from its competition, how long ago the competition opened from them, and just a bunch of different little extra information about like promotions that they're running, what months they're running. So now that we've downloaded and inspected the data sets, we actually just need to upload it directly to Reality Engines. And so in this next box, before we go ahead and click play on this, and while it's uploading, I'm going to just walk through what it's doing. So we're going to call the Reality Engines client. We're going to tell it to create a data set from a local file. And so this is going to give us a reference to an upload. So what we're providing to it here is essentially we're giving it the name. So we're going to call this one the store sales history. We'll give it the project ID we wanted to attach it to, and we'll also give it the dataset type, time series. And so this was from the requirements a little bit higher in this notebook, the special Reality Engines dataset type. We're going to then just open that file as a file object, and we'll just upload the file using the reference to the upload. And so this the Reality Engines API client takes care of splitting up the file into chunks, uploading it to Reality Engines, and then Reality Engines will start, once the upload is complete, it will add it to the project, and then it will start the processing or dataset processing. And so it'll go and featureize the data and start detecting the schema automatically. And again, the second half of this code block is just uploading the store. So we create the store, which is using the dataset type item attributes. And then we'll open the CSV file, and then we'll upload the file to Reality Engines. And then we'll just store a reference to each of these data sets. Again, a lot of information, but we'll get into the next part of this. So now that both of the files are uploaded, we have a blocking code block here, which is going to wait for the data sets to inspect. And so as I mentioned, Reality Engines is going to, for each of these files, inspect the schema. So it's going through processing all of the lines inside of the data set, and it's going to, for each column, give a data type for the column. So this is the last item here. We've got the data types. And so these are just for each column, like what kind of data is inside of that column. So we have identifiers. So that's going to be for the item ID, the store ID. So that's the 1 through 1,000 columns. We've got the column dataset type, which is the the timestamp. That's going to be the date column. We've got the demand, which is the numerical column of how much we actually sold per day. And we've got the customers, which is numerical. We've got the promo and state holiday. And so these were mapped as categorical, which is correct. However, they are missing the column mapping. Since we can't really infer what information you actually are going to provide to us in the future, we do need to actually set these columns to future. So it seems like my second data set is still processing. So I'm just going to give this a second more. I'm sure that with everyone uploading, following along with this, it is taking a little bit longer than it normally does. So we're just going to go ahead and give this a moment to process. But while this is processing, you can just talk about, we can go ahead and even cancel this for the moment, since this is just going to sit and wait for it to be completed. So we'll come back to this block in just a second. So again, as I mentioned, each of these columns have a data type and possibly a column mapping. The column mappings are all from the requirements. I can call the use case requirements that we had called earlier in this workbook, which again just describes all of the possible column mappings that you can use inside of each of your data sets. So in this case, if I get the first requirement, we've got the date, demand, and then also optionally, you can use multiple of the future column mapping. Again, if you had any data you wanted to ignore, we could add an ignore to that column. And then also the item ID. Each of these column mappings have restrictions over what kind of data type you can use. So obviously, if you have a column mapping of dates, you can only have a data type of timestamp. So if you set a column to dates, it's going to override what we detected originally. So let's say we just had like a Unix timestamp, which is just a large number. And we detected that as numerical. We can, if we tag that with date, it will automatically set the data type to timestamp. So we make it really easy to automatically apply the schema to the correct data types when you're using the Reality Engine's column mappings. So seeing these options that are available to me for this data set, I can actually, through the API, set some of my columns to the correct column mapping. So again, as I mentioned, we have 2 columns that are holidays. And so we're going to know what days are holidays ahead of time. So I know when Christmas is, when New Year's is. And so we can use that information, or we can tell Reality Engines about this information that we're going to have in the future, and it will use that as part of training. So it'll automatically split that data off and then use it as part of the predictions. So it can use the fact that it's going to be a holiday as part of the output. So I'm going to go ahead and call the client.setColumn mapping on giving it the project ID. So I've got the forecasting project. I've got the dataset ID that I want to set it on, so the sales dataset. And I'm going to pass in my column name. So I need to get my column name exactly right as I had uploaded it. And so in this case, it's capital state, capital holiday. And I'm going to pass in also the column mapping that I want to use for this column. If I set it to none, it will delete the column mapping that's on it. We also have a separate API call that you can use to just remove the column mapping. But when I hit play on this, it's going to set the column mapping, and then it's going to return the schema after my column mapping has been set. So I've now can see that for my time series data set, I've got all of my columns again, and my column mapping for both state holiday and for school holiday are set to future. And if I wanted to ignore, say, the customer column, so customers might be directly it'd be an indicator of how many sales I'm going to make. I can add a third entry here. I can set my column to customers, and I can set this column to ignore. And when I rerun this, you'll see that's the column mapping for customers is now set to ignore. I've got my future column still. And now I have my entire schema for the time series data set, where I have my store ID, I have my date, I have my sales, which is the demand I'm trying to predict. And then the rest of the columns will be useful for promo as well as holidays. So I'm going to go ahead and check on the status of my other data set. There we go. So I now have processed both my data sets. So you can see my store attributes. My store attributes has the item ID. So that's just going to be the same matching the ID to the store. And then the rest of the information is all just extra information I can use for prediction, or to join on the time series. So all of this information is not going to change over time. It's just useful information that will be applied for the predictions. All right, so now that we've set up our data sets and uploaded them to Reality Engines, we've altered the schema inside of one of our data sets, we can now check to see if we've actually set everything up correctly. So as you can see from the use case requirements call, we have required data types that need to be set. And we also have the data sets that are required in order to actually run. So obviously this project wouldn't make sense if we just added the store attributes and we didn't add the time series. So we have a call in the API client, which allows you to validate the project. And so when you make this call, and I'm going to hit play on this validate, it's going to return a true or false, whether or not the project is actually valid. And if you did have errors, it would show up inside of the dataset errors. And so in this case, if you say unset the item ID inside of store, and you no longer had a store ID column set, it would show up saying that you're missing the item ID column inside of the dataset errors. Likewise, for the other required columns, we have a few other heuristics that we're going to check on each of the data sets. And if you did have any errors that would keep your data set from, or your project from training, they would show up with the project validation call. But since we actually have a true, we can continue forward with training. So now we get to the exciting part. The exciting part is we're actually going to get to check out some of the possible training config options for our deep learning model. So Reality Engines uses a lot of heuristics and is able to actually set most of these, or all of these values for you. But we do provide you the ability to experiment and try different training configs to pass in parameters for your deep learning model. So if you have a little bit more of ML background and you want to tinker around with how the model is going to be trained, this is where you get the information for what you can actually, what levers you can pull and to fine tune your deep learning model. So as I had mentioned before, inside of Reality Engines, we have a bunch of use cases. So we use specialized deep learning models for each of our use cases. So they're going to be different for every single use case inside of our product. So what we're going to do is actually call on our project, we're going to call get training config options. And this is going to give us a list of training config options. This list contains essentially the enum value for each of these options. It'll tell us the data type that we're expecting. So it might be an integer for the test split. It'll tell us what the default value is, and also the range of possible values. So here, our test split, we can go anywhere from 5% of our data is split off for testing, all the way up to 20% of our data can be split off for testing. And the default, again, is about 10%. Again, we can also set the dropout rate, batch size, prediction length. The most interesting of this is actually going to be the prediction length. This is going to be the number of time steps in the future that you want to predict. So by default for this project in this specific data set, we're going to predict 7 time steps in the future. So since we are this data set was automatically detected, if you look just 2 steps down to the forecast frequency, it was detected as a daily entry data set. So we have entries for each day for each store inside of our data set. So in this case, combined with the prediction length, we're going to predicting 7 days in the future. If, for example, we wanted to predict 31 days in the future, we could pass in the prediction length of 31, and that's going to predict 31 time steps in the future. Obviously, when you have a longer prediction length, your error is going to go up slightly as there's less and less certainty over what it's going to look like 31 days in the future versus 7 days from our last data entry for that store. And again, we can also modify the forecast frequency, which if we wanted to say downsample the data set, we could go from 1 day all the way up to, say, we can bundle all of the week's sales, and we can make this a 1 week we can make a prediction for each week for the stores. And so that will bundle a lot of the information together, and we can get a higher level prediction on our data. But for this workshop, we're going to keep it easy. I just want to make you aware of the possibilities if you are a little bit more in tune with deep learning and the possible values you wanted to, or that you could play around with. I definitely encourage you to come back and experiment. This workbook will be available to you after this workshop. And we also provide all of these options inside of our UI. And so you can go ahead and train a new model and play around with these values and see if you can get a higher performing model. So as I mentioned, for this workshop, we're just going to leave the defaults as is. We do get a really high performing model for this data set without having to change anything at all. And so by making this next call, we're going to, on the project object, call train model. And we don't even need to provide the training config options parameter. That will just default to use all the defaults. But if you wanted to provide training config options, all you'd have to do would be to pass in the enum value, say the prediction length, and pass in the numerical value. So if you wanted to up it from 7, you can make it to 14 time steps in the future. And so this will predict 14 days in the future. But I'm just going to hit play to start a model training with the default values. And so this has given me a model object. So we have just our store sales forecasting model. So this has already started training. So we're going to, and so this has kicked off a job inside of Reality Engines. It's going to go and it's going to train a deep learning model given our training config and produce a deep learning model. For this data set in particular, it takes about an hour to an hour and a half. So we're not going to be able to get a trained model until just after the workshop. But you can, just to give you a preview of what the predictions will look like, we can call a model that I trained previously, just a couple hours ago. So I'll explain a little bit more about each of these parameters in just a minute when I get down, but I just want to get you a preview of what your prediction is going to look like. So I'm going to hit play on this, and this is going to instantiate a new Reality Engines client. It's going to call the Get Forecasts API. Given the model deployments as well as the deployment token, which authenticates the model, I get, for my store ID number 1, I get 3 different prediction quantiles, which essentially gives me a high, middle, low of the forecast predictions. And so for in each of these forecasting quantiles, I've got an array of time steps. So you can see for each value, we've got the date, which is my date column inside of my data set. I've got the sales, which is the value I'm trying to predict. And I've got 7 of these. So my prediction length was 7. So for each of these, I can see that my P10 quantile was 2,300, and then 233, 3,945, and again, middle of the road here, I got 2,895, 523, and then the high. So essentially, I've been able to get a prediction with mid, high, low values for each of the time steps in the future. Or in this case, the last value that I had updated for the store was back in 2015, because this is a little bit of an older data set for this store. Now, this next call will essentially just block and wait for your model to finish training and evaluating. You can go ahead and hit that if you want. Essentially, it's going to just sit and wait for the next hour to hour and a half for your model to train. So for this point going forward, I'm actually going to ask that you go ahead and pop back to the Zoom if you are currently in your workbook, because I'm going to go ahead and load up a model that I trained a couple hours ago, and then we'll actually go through and I'll show you what the next few steps are going to look like as in part of the actual deploying of your model, and then be able to make live and also batch predictions. So I'll give everyone just a moment to hop back over to this screen. And so you'll notice that I included a step here called checkpoint. So these notebooks will continue to run and sit and wait for your model to finish training for an hour or two. But if you do click off or click refresh, or you leave this page and come back and you want to pick up where you left off, you don't need to go through all of the previous steps. This code block here inside of checkpoint will actually perform the Reality Engines import, installation, and then also taking your API key, and it'll go through your projects inside of your inside of Reality Engines and pick out this forecasting project, and then it will go ahead and check to see if the model is done training. So I'm going to go ahead and switch over to a workbook here that is fresh. I just refreshed this page, so I have not run any of the previous steps. I'm going to go ahead and zoom in my screen here so you can see the text a little bit better. I'm going to then open this checkpoint. I'm going to hit play. And again, I get prompted asking if you want to run code written by me. I'm going to accept, and then it's going to reinstall the Reality Engines client. It's going to use my API key, and then I now have my trained model. So again, this wait for evaluation will block and wait. So if you come back and say 15 minutes and it's not done training, this call will continue to wait until you are ready to go. And so now we're going to check out to see our model metrics to understand if how our model did. So we, as I mentioned, as part of the training config, we actually split off a certain amount of data that we use to evaluate our model to see how well our model did at predicting values into the future. So by calling the model get metrics, I'm actually going to get two values here, the normalized root mean square error, as well as the symmetric mean absolute percent error. And we have descriptions right below. Essentially, the normalized root mean square error, or NRMSE. It's, as Salmon mentioned, just a metric to measure forecasting error and calculate the difference between the predicted value and the values that were inside of the data set. And inside of our test split of the data set. So we want to get a low value here, as low as possible. And so we did get a NRMSE of 0.2, which is pretty good. And then we got a SMAPE, or the symmetric mean absolute percent error. And so this is just calculating the average difference between the prediction value and the actual value inside of the data set, inside of our test data. And so these metrics were pretty good for this data set. So we're going to go ahead and say that this is a good model, and we actually want to deploy it into production. So to go from a trained model to actually deploying it is really easy inside of Reality Engines. Essentially, for each of our models, or for a trained model, all we have to do is call create deployment on it. And so this is going to spin up resources inside of Reality Engines to actually host your model. And this is where you can actually start making predictions on the model in both real time as well as in batch predictions. And we'll go over the difference between the two in just a second. So I'm going to hit play on this next box. And again, you'll be able to go through all of these steps yourself as soon as your model is trained. You will receive an email when it's done. So if you want to just keep this workbook bookmarked, you can come back here and continue along with these steps. So the deploying model, again, is reserving some machine to host your model. So it's going to take just a moment to spin up those resources. But once this is done spinning up, we'll have a deployment available to actually start making real-time predictions on. And so the next step right after that will be to create a deployment token. So for every part of this the process up until this point, we've used the API key to authenticate all of your requests, and that's because all of these are creating, uploading, and training, which is all long time and expensive processes in terms of the amount of time you're investing in it. And so you want to use your API key to authenticate all of your requests to make sure it's you. But these deployments or models, you actually want to make predictions. You could want to keep them internally, in which case you could use your API key, but your deployment token will allow you to publish your essentially be able to run this anywhere. So whether you're embedding it inside of a website, a mobile app, or using it inside of your own servers, you can use your deployment token to authenticate the request to make that real-time prediction. And so that's how you're able to then make a forecasting prediction inside of, say, a consumer finances app. And so you can embed that directly in, and the end user could get a bunch of forecasts for their current financial situation directly from Reality Engines. So again, it should take just about a minute to a minute and a half to actually spin up this deployment. And once we've done that, we can then create the deployment token. And so the deployment token is project scope. So if you do have a bunch of deployments inside of your project, say you have like a test or different, you want to A/B test between your deployments, you can use the same deployment token to authenticate inside of your project. And so while that's spinning up, I'm just going to the pre-hit play here, and so that'll run as soon as the deployment is done being created. And so while that's going on, I'm going to go ahead and walk through the what the predict is going to look like. You did see the example prediction from my own deployment earlier in the workbook. And so we were able to embed that without using an API key and call that as it's in a different project from what you're, or a different organization from what you were using, because all of the prediction API calls are authenticated through the deployment token. So for each prediction call, you're just going to call the relevant prediction API. In this case, it's get forecast for the retail or demand forecasting API. And you're just going to pass it the deployment token as well as the deployment ID. So again, once this deployment is done spinning up, we're going to just pass in the identifier for this deployment. And then we're going to give it the query data. So the query data is just, in this case, the store ID. So by providing just a store, it's going to load up the history of that store. And then we're going to use that information to make predictions on the next 7 steps into the future for that store. If you wanted to provide additional future data, so let's say the next 7 timestamps, we actually have a holiday that wasn't in the training data set that we had, we can provide that information as the next parameter. So we have like a future data here. Since this isn't auto-completing, I believe it's, future data, and you can pass it in as well with the specific holiday. So you have the state holiday and the school holiday, and so you can mark each column with the appropriate holiday. So now that we have our deployment, now that the code block above has completed, we have the deployment token, which we'll use for the prediction. So I can finally make a forecasting call with my deployment token. And now I have predictions on my trained model. And so because we are running a bit short on time, and I want to make sure that we get to the anomaly prediction or anomaly workbook, I'm going to skip this section to actually run because it does take a few minutes to actually run to completion. But essentially, the call above, the get forecasts, allows you to make a real-time prediction. So I want this prediction for this store right now. But I do have 1,000 stores. So let's say that I wanted to just do or get predictions for all 1,000 of my stores and get them all into one file. All I have to do is call the batch prediction API. And so this will actually, given a deployment, will make prediction using our trained model on all of the IDs in my data set. And so then we can, at a later time, then just download that file that's been generated, which has all of the predictions for all of my stores. And I can see each of the time series forecasting, and then I can use that inside of a business process or to use as part of my sales forecasting report that I'm presenting to my CEO. So with that, I'm going to go ahead and pass over the mic to Yash. We have a link in both the top and bottom of this workbook, which is the bit.ly/R_E_anomaly. That's lowercase anomaly. And you can go ahead and just click on that, and that'll bring you to the Reality Engines Anomaly Workbook. You're going to want to grab your API key that you used in this workbook, so you can scroll up to the top, grab that API key, or just click on the links inside of the Anomaly Workbook. We do have the API key links, so you can click on your API key dashboard and bring it in. So with that, I'm going to pass the mic over to Yash, and he will take you through the Anomaly Detection Workbook.
Thanks, Austin. So yeah, let me share my screen. Okay. Can you guys see my screen right now?
Yes.
Cool, awesome. So yeah, so thanks, Austin. So now that you've had some experience building your own forecasting model, I'm going to show you how to build your own anomaly detection model. So if you go ahead and click the link in the forecasting book, that should take you to this workbook here, which is the anomaly detection workbook. Again, this is bit.ly/R_E_lowercase anomaly, and you should be able to see this workbook here. Yeah, so in this workbook, we'll be training an anomaly detection model on some realistic cloud spend data. So the idea is you have a fire hose of data coming in through a cloud server like Amazon AWS, and you want to identify when there are certain spikes or when there's random behavior in the cloud spend, so you can adjust for it, or you can see when that happens immediately or when it has happened in the past, and use that to make decisions. So this is that we're going to be using custom data set, the cloud spend data set, which you can find, which we provided here for you. And we'll be using pretty much the same process that Austin described to get started up, with a few changes to account for this new type of data set or this new type of use case, which will be the anomaly detection use case. So we'll get started. We will, of course, start running this notebook, install Reality Engines. Again, it says that this notebook was not authored by Google and it was authored by me, but we want to run anyway. So we'll let the model run, and we'll see that we can install. We'll install Reality Engines, which will have the client API that we need to train the anomaly detection model. Then we'll also import the other data sets and libraries that we'll need: the pandas library, the pretty print library, similar to Austin, similar to Austin's notebook. And finally, we'll also have to use the same API key that Austin showed you how to get. Again, you can click this link to get to the API key. I have created one right here, so I shall use that one. Again, just go to the API key in your profile. So you should be able to go to API keys in your profile on Reality Engines and find this API key here, or create a new one if you don't have one. But we can go ahead and copy this one and paste it here. And that should be sufficient to instantiate our client with. So we'll go ahead and instantiate our Reality Engines client with this API key. Yeah, this should be pretty much identical. This is identical to what you did for the forecasting use case. So we're going to go a little bit quicker through this. And yeah, so once you've instantiated the client, you can go ahead and list all the projects in the same way that Austin showed you. For this use case, instead of doing retail, we're going to use operations incident, because this use case is particularly tailored for anomaly detection and specifically time series anomaly detection, which is what we need here. So we're going to use the operations incident use case this time. We'll go ahead and set the variable use case to equal to operations incident, and we'll take a look at what the requirements for this use case are. So for the operations incident use case, there are two data sets that you can upload and that you can use. There's only one that's required, and that's the time series one. And this is pretty similar to the time series data set that that you saw in the forecasting or the retail use case. Here we have a date column, which will be the date, the day, year, month that corresponds to the value, and the item ID that will be the actual items that you're trying to identify anomalies for. So in this data set, we're going to have two cloud services, Amazon EC2 and Amazon RDS. And for each one, and there'll be a column that identifies which row corresponds to the EC2 instance and which row corresponds to the RDS instance, and that would be this item ID column. And for the date, we'll have a usage start date, which will be the date. We also accept another data set, the item attributes data set. So for instance, if you have any additional information that is not based on a time series, that may be based on a non-time series data, like information about the type of services or like, how much usage there is or something in like that's independent of time series, you can upload that there and the model will automatically use that data to identify anomalies. So this is one of the benefits of using a deep learning model, because in a classical non-deep learning model, you'd have to like build specialized tooling and models for each one of these extra columns. But in deep learning, we can just like automatically use them and have the model figure out which fields are important and which ones are not. So yeah, so basically these are the two data sets that we allow you to upload. The only one that's required is a time series one. And for this use case, for this workshop, we're only gonna show off a data set with a single data set, which is a time series data set. So we'll go ahead and create a project. So the project we'll call it Cloud Sven, because that's what it is. And we'll make sure that the use case is operations incident as it is. So the next thing to do is to actually add the data set to your project. And like Austin mentioned, you can use S3 or Google Cloud Storage or any of the other blob storage services to upload your data. But instead of hooking your S3 account to Reality Engines, we will just use the data that we'll download from into this workbook. So let's go ahead and do that. So this site here has the actual data that's available, and we'll go ahead and read that data and take a look at it just to give you a sense for what this data looks like. And like I mentioned, we have 3 columns here: a usage start date, a service, and a blended cost. The usage start date is obviously the date column, which will indicate when this cost was incurred, and the service will indicates for what service this cost was incurred. So for a single row would be for a given service. So taking this row for Amazon RDS on the 1st of Jan 2019, the blended cost was 1,326. And this data set is for educational purposes. It's built to look realistic. So it has like realistic features in it. And this is something that like we want to show off that we can actually train a model on this problem or on this data set. So if we go ahead and go through the next step of anomaly detection, the next step was visualization. So we'll go ahead and visualize what this data looks like. And as you can see, there's two columns here. One is Amazon RDS and the other is Amazon EC2. The Amazon and each of these have some blended costs across time. And as you can see, there seems to be a spike here, and this spike is maybe something that we want to evaluate our anomaly model on, because if the anomaly model works correctly, then we should see the anomaly score or the reconstruction error go up when we see this time series right here, or this spike right here. So now that we visualize the data, we can go ahead and upload this data to our project. So we'll go ahead and upload this cloud spend data set into the project in the same way that we did for the forecasting. So yeah, we'll give it a couple of seconds. And okay, it looks like the cloud spend data set has been uploaded. So now we can go ahead and check the status of this project or of this data set. So we can give this a few seconds, and ideally we should be looking for the schemas, and we should be looking for the mappings that seem correct. So this goes back, this is the same as the forecasting use case, where the reality engines will automatically figure out the data type for each column. So as you can see, usage start date was correctly identified to be a timestamp column. The service was correctly identified to be a categorical column, and the blended cost was correctly identified to be a numerical column. And that is as we need, because we will be using these columns to do our anomaly detection, to build our anomaly detection model. The next thing that we need to do is actually assign the item IDs or the column mappings to each of these columns in the data set. So as I mentioned before, there was a date column that was corresponding to the date that we needed. So that would be the usage start date here, would be the date column. The blended and then we have an item ID, and this was the same as the service column here, as I mentioned before. So yeah, we'll go ahead and do that. We'll set the column mapping so usage start date is a date and the service is an item ID as required. And once we do that, we'll see correctly that the schema has changed and updated. So usage start date was correctly identified to be a timestamp column, have data type timestamp, and is mapped to the date column. The service was correctly identified to be an identifier. Now that it was incorrectly identified to be a categorical data because we wanted to use as an item ID, so it got updated to be an identifier. And of course, blended cost stays numerical, and we don't want to map it to anything because we want to actually use that to be we want that to be the value on which we are identifying anomalies. Cool. Once we've done that, we can go ahead and start to train the model. But before we go ahead and train the model, we want to validate that everything is ready to be trained, and it looks like it is. So it looks like the data, at least for me, has been set up and is ready to train. I think if you follow through all the steps here, it should also give you a valid true. If not, again, we have people on the Slack channel and on the Zoom Hangout that can help you if you need that help. And again, like the forecasting use case, we have a couple of options for you to configure if you have if you want to change some of these, or if you have more machine learning expertise, the dropout rate, the batch size, and the test split. For now, we're going to leave these as a default and continue training our model. So we'll go ahead and train our model. So this will be this will be the VAE model. So just to give you a little bit of background on what this model does in the back end, it goes ahead and takes slices of this data set. So it'll take like a small chunk here of maybe 3 days, and it'll use a RNN, or recurrent neural network, to try and recreate that data. And it uses the VAE, as I described in my talk, to try and recreate that data. And if it can recreate that data well, then we'll assume that it's part of the anomaly. Sorry, it's part of the normal data. And if it can't reproduce the error well, then we'll assume it's an anomaly. So in this use case, we might see, like, since we see a lot of these data points, we might assume that something that looks like this is not an anomaly because you've never seen it before. So it's really easy for the VAE to recreate a window here or a window here. But when we go here, we'll see that, hey, suddenly the data spiked, and the VAE has never seen something like this before, or never seen a time range that looks like this before. So we should classify this as an anomaly. And that's something that we're hoping to see from this model. And yeah, so again, this will take a couple of maybe like 20 to 30 minutes to train. So I will let this train. And if you let this train, I think by the end of this talk, and maybe a little bit after, this model should be trained, and you can run, you should be able to use that model in practice. But again, I just want to go ahead and show you what the predictions for this model will look like. So if I go ahead and run a model that I've already pre-trained for you guys, you can see that, you can see that you can call a predict function on our method on the client without using an API key. And as long as you have a deployment ID and deployment token, based on the stuff that, based on the deployment, then you should be able to get these results. The first thing you need to do is like make sure that skip histogram is false, and that gives you histogram of the data. So as you can see here, the anomaly scores go from 0 to 1. So the reconstruction loss, that is, goes from 0 to 1. And you'll get a sense for every, so this is like, so each label here is a percentile label. So so this is a 10 percentile. This is like the 10th percentile. This is the 20th percentile. This is a 30th percentile, and so on. And then this is obviously the 100th percentile. And the idea is this gives you histogram, so you can tune your threshold. So most data points will have an anomaly score that is like approximately 0.09, which seems about correct. So it has a very slow reconstruction error, a very low anomaly score. Anything above 1, it seems like, will have a high anomaly score, and maybe something that we want to flag as an anomaly. And once we see this histogram, we can select a threshold that we like. And in this case, it might be 0.1 or something. And we can run this model with a, by changing the threshold and running it with the new threshold. And if we go ahead and do that, then you should see that a bunch of new data points that all have anomaly score greater than 1. So to understand this, what you end up with is a JSON data set where you have a list of items. Each item includes a service name, which in this case is RDS, and in the next case is EC2. And for each item, you get the blended cost for a usage date, for a usage start date. You get the blended cost for that usage start date and an anomaly score for that usage start date. So these are all the points that had an anomaly score greater than the threshold, and that is something that we want to. These might be the points that we want to flag, and these are the points we might want to identify as anomalies for our use cases. But yeah, again, this is a model that I pre-trained, but if you go ahead and you continue and you run this, you should see, you should like have a model that trains and gives you results exactly like this. And if you use your own deployment ID and deployment token, you should see that too. The next step is something that will just block on the model training. So this might take a while to train. So here you can block and wait for the model to train. However, I've already got a pre-trained model. So I'm going to go ahead and use this pre-trained model with this pre-trained deployment ID and deployment token to evaluate the model and see how you might be able to do that. Again, as Austin mentioned, you can go ahead and if for some reason your notebook gets canceled or refreshes, you can always go here and insert your API key here and pull that pull the model that you've been training that you've been training and continue along from this point forward. Once you have the model that's trained, you should be able to get evaluation metrics. So, So in this case, the actual model is still being trained, but once the model's trained, you should get evaluation metrics. And these metrics, you'll essentially get a mean, a standard deviation, and a percentile score. And the mean and standard deviation are just the mean reconstruction error. So essentially what you get from the metrics here is the same thing as you got from the histogram from the predict thing. So you'll get a sense for how many points your model was able to reconstruct and at what anomaly score that reconstruction happened. And that's something that you might want to see, because if you have the mean of your anomaly score is too high, then it might mean that your model wasn't able to reconstruct or wasn't able to fit the data well, and you might want to train it for longer, or there might be some other issue in the model. So the metrics will help you get a sense for what that model get a sense for get a sense for like how well the model has fit the data, or how well the VAE has fit the data. And as I showed before, this will essentially be the same thing as histogram here. So you basically want to see something where the mean is somewhere around like 0.0 something, because if it's too large, then you're going to end up with a model that doesn't know how to fit the data. And yeah, once you have that ready, then you can go ahead and deploy the model. This is the same. This goes through the same process that again, my model has not completed training, but once the model has been completed training, this is the same thing as the forecasting use case, and you will get essentially a deployment token and a deployment ID that you can use to run this predict API. Finally, we're going to go ahead and actually evaluate our model and predict our model. And in this case, we're not trying to just see how well our model, not trying to see the histogram of our model, but what we actually want to do is see how this model performed on this spike here. So if you see the spike, it looks like the spike happened like in the middle of 2019. And we want basically to identify the spike and try and find the points at which we want to see the anomaly score across the spike. So we can go ahead and run this. And what we should see is something that looks like this, where the red line here shows the anomaly score, and the ticks on the right show the anomaly score from 0 to 1. And the ticks on the y-axis, on the x-axis show the date. So again, this goes from middle of 2019 onwards. So this is like the same spike that we saw up here. And we just isolated that time slice that we want to evaluate this model on. On the right, in the blue line, we see the actual, we actually see the blended cost over time. And the red horizontal lines indicate the levels of the histogram. So this would be the 0th percentile, this would be the 10th percentile, 20th percentile, 30th percentile, and so on. So as you can see, like most of the data points fit within the top 90 percentiles, and very few go between 90 and 100 percentile. But as we can see here, and as it's expected, the anomaly score stays low across the entire percentile and then jumps up for this anomalous time slice here, and then goes back down and stays considerably non-anomalous for the rest of the time series. And here, what we're doing is we're just taking the min start and max end, which are 2 dates, Unix time dates, and we're just selecting a window within those min, start, and max end time dates to expand the time series and to make sure that we have anomaly detection working for a specific window in that time series. Again, if we do 1 here, we should be able to see the EC2. So this takes a little bit of time to run because we have to go and run the VAE on the entire time slice data. But once you get it, you get a sense for, again, this would be the same time slice for EC2 here. And as you can see here, there are like some, the EC2 data set has this weird thing where it has like a downward trend. And at some point, this downward trend becomes much lower than like the normal in this part of the data set. So we should correctly identify everything here as an anomaly. And that is what we see here. Of course, none of these data points are as anomalous as the spike we saw for the RDS data set or the RDS service, but they are, but there is some anomalies here that like you may want to keep, that you may want to track. Yeah, so I think that's it. There's, you can go ahead and play with this model as you feel like. Once you have your own, deployment, once your model has trained and is ready to use, you can go ahead and deploy it. You can deploy the token, and then you can go ahead and use this block of code here to go and visualize different parts of your time series to see the anomaly score and to try and identify anomalies. One thing to keep in mind is that this model does assume that these two anomalies are related in some way. In this case, they were not related, but because the model takes both of them in and considers both of them when trying to identify anomalies, you might see a point where, which may not look like an anomaly to you, but if you look at a bunch of different data sets, it might seem like there was a correlated anomaly score across all the data sets, and that might actually be correct. And of course, you can go ahead and tune this model using the threshold and using other parameters. You can add additional data. So if you have additional data about EC2 and RDS other than just its name, you can go ahead and add that data as an item attribute data set, and hopefully you'll have a model that can work well and that you can use for identifying anomalies in time series data. Yeah, I think that's all I have. I will hand it off to Bindu right now to wrap up and talk a little bit more about Reality Engines.
That's great. Thank you, Yash. And thank you everyone for joining the workshop today. I just had a couple of comments. The first thing is most of you created an account on Reality Engines. That's a beta account, and that is free of charge. So you will be able to run models from our sample data sets, as well as upload your own data sets and run models for free during the beta period. You can always come back to it anytime. So you've created it with your own username and password, so you can access it, as well as also invite others in your organization. So one of the key parts of this account that we gave you is that you can actually invite any number of team members to collaborate with each other and create models. If you want to talk to one of our ML specialists, you can also do that by clicking on Contact ML Specialist from the service itself. We run a bunch of different workshops as well as AI meetups. So we're hoping to see you again on our next workshop. Yeah, drop us a note. We're easy to reach. My email is bindu@realityengines.ai, and we'll be happy to help for any of your AI needs. Thank you. Oh, how long is the free period was the question. The free period is at least for the next 8 weeks. I can't give you an exact date where it'll end, but it should be available for free for the next 8 weeks. Any other questions you may have, you can also drop us a note. Again, bindu@realityengines.ai, and you can also find me or any of us, Yash, Austin, Sam, on LinkedIn, and I believe most of us also have Twitter accounts. So yeah, we'll see you online, and keep safe, and thank you for joining. Bill, did you have anything else?
Okay, great. Yeah, I think just quick. We have a few more minutes. Can you quick check if we have all of the questions answered in the chat?
Yeah, I'm looking.
Yeah, just a quick scan to see if any of them. And we also have some questions on the YouTube. I copy paste to here in the chat. So if you see have not been answered, maybe you can just say a few words on that.
Got it. So actually, I will read this out. Can you list all the services we used? We didn't use many services except RealityEngines.AI. The data was, you can get that either from, you can load up your data either through a CSV file. So you can just use a simple CSV file, which you have on your local box, or you can store the data in an S3 bucket or a GCP bucket for now. So you can go through that. What will be your business model? Yeah, so right now it's in the beta phase. So like I said, it's free. Our business model, when we actually go into GA, general availability, will be very similar to any of the cloud services that you may have used. So if you've used AWS, I see a question here around Redshift, but if you've used AWS or GCP or Azure, it's all pay as you go. So we'll have a very similar business model. We'll have a free tier. So you can use the free tier until you hit a particular limit. And beyond that, you'll be charged on a per usage basis. This is very unique in this space because most of these other enterprise companies or enterprise AI companies have a lot of upfront money that you have to pay. In our case, you don't have to pay anything upfront, and you only pay mostly for predictions. And so it keeps us kind of on our toes because we want to make sure our predictions look good for you so that you can continue to use it. Where can I find the posted meetups, workshops to register? So we do a bunch of them through Bill's organization, AI Camp. So you should definitely, and I guess most of you are members of that, so you should keep a lookout for that. We also have some on our own website. So if you go to RealityEngines.AI, you will see a meetup. So you can go there. There's also a YouTube link. We have a YouTube channel if you want to participate. You can subscribe to that, and we do some workshops through that as well. Okay, let's see. I think that should be, I mean, Korea, would it be a good idea to split the data set into one for Amazon EC2? Yeah, so the question around splitting the data set, it's actually better to have your data together because the VAE will learn across these different time series. So we were talking about cloud spend here across various different services, right? EC2, RDS. So the more services you have, the more regions you have, the more, the better it is to add that into one data set. There's a question around deployment ID. So the way you get your deployment ID is only after you actually deploy your model. So first you need to train your model. The training takes a few minutes. My guess is, I'm not sure, but my guess is that most of your models are still in training. So once they finish training, you'll get an email. So check your inboxes. It'll say training completed. Once you get that, you can click back to the service. At that point, you'll want to deploy your model. And that can be either through the console. So it's very easy to deploy it either through the UI or through the API, through the notebook. You can come back to your notebook and hit deploy model. And that's when you get your deployment ID.